In this video, we'll explore the perceptron, which is a fundamental building block of deep learning and essential for understanding the basics of deep learning. A perceptron is a basic building block of artificial intelligence, inspired by human nerve cells or neurons. The fundamental structure of a perceptron consists of input values, a linear combination of those inputs, an activation function, and an output value. Imagine you have two input values, x1 and x2. Each of these inputs is multiplied by its corresponding weight, weight 1 and weight 2, then a bias b is added. After that, the result passes through an activation function, and finally, a y value is output. In early perceptrons, the activation function used was a step function, which produced outputs of either 0 or 1. Here, the weight is a value multiplied by each input, determining how much each input contributes to the result. The bias, on the other hand, is a constant added to the weighted sum, which allows the model to adjust the decision boundary and learn more flexibly if the weights alone aren't sufficient. In other words, it helps adjust the output even when the input values are 0, independent of the input data. Let's explain the structure of a perceptron with a simple example. Imagine a person named Brian is deciding whether to buy a product. His decision is based on two factors, price and quality. However, he considers price more important than quality, so he assigns 50% importance to price and 10% to quality. Now let's introduce some unexpected factors, such as sudden medical expenses or receiving a bonus from work. Taking all these situations into account, if the total cost is less than his planned budget, he decides he will buy the product. If it exceeds his budget, he decides he will not buy it. If we connect the example we discussed earlier to the structure of a perceptron, the price and quality represent the input values, x1 and x2, while the 50% and 10% importance factors are the weights. Unexpected expenses like medical bills or bonuses represent the bias. The decision of whether the cost is smaller or larger than the budget is like the activation function, and the final decision to buy or not is the output. Applying this to a perceptron, you multiply each input by its respective weight and add the bias, resulting in a value of 0.7. The activation function will output 1, which means a decision to buy if the value is greater than 0, and 0 meaning no purchase if it's less than 0. Since 0.7 is greater than 0, the activation function outputs 1, leading to the final decision to buy the product. However, the perceptron has clear limitations. In this diagram, let's say the red represents will buy and the blue represents will not buy. Some people may only buy when both the price and quality are good, while others may not buy if both the price and quality are too low. For such simple criteria, an original perceptron can effectively determine whether to buy or not. But in other cases, someone might not buy if both the price and quality are low, or even if both are too high. In these cases, it becomes difficult to separate the decision to buy based on just one criterion. In other words, the traditional perceptron provides only one decision boundary, so it has clear limitations when it comes to solving problems that require making complex decisions based on multiple factors. However, the perceptron has clear limitations. Let's consider the limitations of this perceptron based on the four basic logic operations. For the AND operation, the output is 1 only when both inputs are 1. NAND is the negation of AND, so the output is 0 only when both inputs are 1. For OR, the output is 1 if at least one input is one of the inputs is 1. For XOR, the output is 1 only when the inputs are different from each other. Since the original perceptron can only form a single decision boundary, it can solve problems like AND, NAND, and OR. But it cannot handle more complex problems like XOR. Here's how the XOR problem can be resolved. In the first step, we perform NAND and OR operations on the input values. The NAND operation outputs 0 only when both inputs are 1 and outputs 1 otherwise. The OR operation outputs 1 if at least one of the inputs is 1 and outputs 0 only when both inputs are 0. In the second step, we take the results of the NAND and OR operations and use them as inputs for an AND operation. The AND operation outputs 1 only when both inputs are 1. By setting up these operations in separate layers, each with its own perceptrons, we can solve the XOR problem. These layers are called hidden layers. This approach shows why introducing a multi-layer network structure is necessary to overcome the limitations of a single perceptron. In this diagram, the circles represent individual perceptrons, which are also called nodes. A perceptron is therefore a fundamental building block of neural networks. Each node receives input signals, applies weights, and produces outputs through an activation function. By increasing the number of nodes or the number of hidden layers, we can solve more complex problems. The hidden layers are situated between the input and output layers and play a crucial role in solving nonlinear problems. By stacking multiple hidden layers, we create a multi-layer perceptron, which is used to tackle more complex issues. This structure is similar to the human nervous system and is therefore referred to as an artificial neural network, or simply neural network. As neural networks evolved to include multiple layers and handle large amounts of data, the term deep learning emerged. Deep learning utilizes deep neural networks to solve even more complex and sophisticated problems.